today, Hyunbae will give us a talk about the role of IGM in this high redshift era in terms of Lyman alpha observation, I guess. Yeah, let's please join me welcoming Hyunbae.
Okay, thanks everyone for coming. Yeah, it's my great pleasure to be here. I always wanted to be here. It's my first time. I'm really enjoying my time here. Thanks to this warm welcome by Junseop, team, and Tepe and so on. Today I'll be talking about my most recent work, which I'm most interested on. Basically, Lyman alpha as a probe of how to probe reionization error with Lyman alpha. So just to start with the basics, touch on the terminology. Cosmic reionization, I guess most of you know, it's an early period in the cosmic history, roughly between redshift 30 and 6, or 10 to the 8 and 9 years after the Big Bang, when the first generation of galaxies, early galaxies, were ionizing the intergalactic medium. Right? You know that universe recombined, all the baryons recombined into neutral hydrogen helium when the redshift was 1000, but we know that in today's universe, in the intergalactic space, all the baryon is ionized. This is when the transition happened, right? So we think it happened in somewhat in an inhomogeneous manner where early galaxies started emitting UV light, ionizing radiation, then they formed H2 regions around them first, and then over time, as they emit more and more ionizing photons, these bubbles probably grew over time, and at redshift of around 6, they overlap with each other to complete this phase transition. Now, this era is becoming more interesting because now, especially the baryonic part of the universe, is highly nonlinear, difficult to simulate. But thanks to recent progress in our numerical, computational power, we are kind of becoming able to simulate some of this universe to some extent, especially in the baryonic sector. And at the same time, we have this state-of-art instrument from the observational side, such as James Webb Space Telescope, which is finally opening a huge window to this very high-res universe. So this is now becoming an interesting era where observers and theorists can sit together and discuss on the same objects. So now observers bring these interesting observations, and as a theorist, I look into my simulation and say, okay, this must be that, and blah blah blah. Whereas in the past, theorists would simulate redshift 20 universe, observers would observe redshift 1 universe, and we never get to talk to each other. So most of my work is done in collaboration with my observer friend, weekly meeting, and I think it's a very interesting topic. So why Lyman alpha emission? So Lyman alpha emission is mostly emitted from star-forming galaxies, ionizing gas. In the star-forming region, there are a lot of massive short-lived stars with very strong ionizing radiation. They ionize gas. When the gas recombines, a lot of them get converted into Lyman alpha photons when they go to 2p state of the hydrogen atom. Right? So if you look at some of the low redshift, highly star-forming galaxies, you very often see very strong Lyman alpha emission line like this. I give you 3 examples here. They have very different shapes. Sometimes it's single-peaked. Sometimes they're double-peaked. When they're double-peaked, that means you have less flux at the center, the resonance, because neutral hydrogen can easily trap Lyman alpha photons and make them scatter inside the gas cloud. But so in order to escape such dense H1 cloud, they have to kind of scatter away from the resonance. So often the time you see this kind of double-peak, bit away from the resonance. So why this is interesting in the reionization? During reionization, a part of IGM is neutral, right? And ionized, right? So when this Lyman alpha emission line enters neutral part of the IGM, now they're going to be attenuated according to the geometry of the ionized region. And based on the attenuation, we can kind of put a constraint on the process of reionization. That's the basic idea. So here is giving you some demonstration. Suppose now this single peak, this blue dashed line is what is originally emitted from the star-forming galaxy. then if this galaxy is early in the reionization epoch, or if it's from a fainter galaxy, then the H2 bubble surrounding the galaxy would be small. Then what will happen is on the blue side of the emission, they're going to be like all stripped off, because the blue side will eventually redshift to Lyman alpha resonance. And if you look at the cross section, of course, at the resonance, the cross section is very high. So every photons that will go through the Lyman alpha resonance gate will be removed. On the red side, they will escape initially, but then when they enter the neutral region, now the damping wing part of the cross section will be so large in the neutral region with high H1 density that this damping wing also will suppress some of the red side photons. So, and this suppression on the red side will depend on the size of the bubble, because if the bubble is bigger, you redshift more away from the resonance, and therefore you are hit by the weaker part of the damping wing. But if the bubble is smaller, then you are hit by the stronger part of the damping wing. So we expect to constrain the bubble size around these star-forming galaxies by statistically measuring the strength of this Lyman alpha emission. That's the basic idea people had in mind. And of course, some observations have been done. This is one of very high redshift observation done by a ground telescope, Keck telescope in Hawaii, at redshift of 7.5 by my friend in Daejeon. So basically what you're seeing here is this black solid line is the signal, and you can kind of see this distinct peak fitted by this red line, which is basically the Lyman alpha emission transmitted through the IGM of redshift 7.5 galaxies. And you have other lines basically showing how noisy this spectrum is because of these atmospheric noises. Right? But basically that's the idea. So this is showing you the fraction of strong Lyman alpha emitting galaxies at different redshift. You can kind of see up until redshift 6, you see more and more strong Lyman alpha emitting galaxies, because as you go to higher redshift, more galaxies are star forming. But above redshift 6, you suddenly see some steep decline in the Lyman alpha emitter fraction, indicating that the reionization must be happening there. Some part of the IGM was neutral, and probably statistically most of the Lyman alpha emission lines are attenuated strongly. So people have been doing a lot of modeling to convert this Lyman alpha emitter fraction into the global ionization fraction of the IGM at different redshift, therefore constraining the reionization history. Now, of course, in the future is very bright. We'll have more telescopes, right? We have JWST, which some of which observation I will introduce today. We have Euclid, which already launched and is commissioning, and then we have Roman telescope, and there will be also a lot of big, giant, large aperture ground telescopes being built or planned, right? So we'll definitely have much more data from this high redshift universe. And now that means also for theorists, there are a lot to do. So I'll briefly list the content I'll be describing here. There are like 6 items I'll be discussing regarding the Lyman alpha emission from the reionization era. I'll go one by one. Basically, there are a lot of interesting stuff, right? Lyman alpha peak offset, and then the redshift and brightness dependence, which I just mentioned in the picture, and also there is a lot of the variation in the sightline. Sometimes we see a tight Lyman alpha emitter cluster at high redshift, and also sometimes there is a double peaked Lyman alpha emitter at high redshift. Explain why that's interesting. And also apart from the Lyman alpha emission line, also we see a damping signature of Lyman alpha damping absorption in the extended continuum from space telescope, which is another interesting probe. So I'm a theorist. I work with simulation, and I showed you some schematic picture, which is mostly conceived by the observers. But if you look at the simulated universe, it's definitely much more complex than what you imagine in this schematic picture. So in this simulation, we are trying to come up with some realistic realization of the reionization era by simulating this ionizing radiation from early galaxies. We initialize the box in 64 megaparsec in a cosmological size in a high resolution of 4,000 cube grid. And then when the dark matter halo forms, with some prescription, we attach some ionizing radiation to these early galaxies and then run radiative transfer to simulate how the intergalactic medium gets ionized by this ionizing radiation from early galaxies. And then, of course, we also put a lot of baryonic physics, such as stellar feedback, supernova feedback, and so on, to make it as realistic as possible. So the motivation here is, okay, we know that this is probably not same as the real universe, but much better than the schematic you had, right? So we are going to see how the Riemann alpha emission from this complicated IGM looks like, and whether they can explain a lot of stuff we've been seeing in the observation. So just for another demonstration, here's the zoom in of the neutral hydrogen density map from the CoDa simulation at 2 different snapshots. So in the left, I'm showing the full box where we have multiple H2 regions from different galaxies. And if you zoom in to the maximum level, this is 1 megaparsec box. We are really resolving the video radius of individual halos and all these filamentary structures surrounding them. And of course, from redshift to 7 to 8, also we are simulating the realistic growth of H2 bubbles. Okay, so here is what I'm going to be doing. So the emission from the galaxy, we are not going to be able to model. We do not have high resolution inside the galaxy. We have high resolution in the intergalactic medium. So we are going to assume Riemann alpha emission emergent flux from individual galaxy with some simplified model, just double peak symmetric, right? This can be changed anytime. And then what we will be actually calculating is the transmission curve, the part that IGM allows transmission. So basically, you multiply this transmission curve we calculate from the simulation and multiply that to the emergence flux, then we get the transmitted flux over here. This will be actually a mock observation that telescopes will see, and we calculate from our simulation. So here is a demonstration with the movie. So this is a video radius around the halo, and this will be where I start this triangle. And then basically calculating Riemann alpha transmission means you are just integrating the opacity. You have H1 density from the simulation. We know the cross section of the Riemann alpha. Basically, you integrate that along the line of sight. So if I were to play the movie, yeah. So as you fly in the intergalactic medium, you see what was initially double peaked profile gets stripped away, and basically you are left with some remaining transmitted flux, right? So if you look at in detail, you can see as you go along, as the profile redshift, the resonant part gets completely observed over time. And when the line of sight enters the blue region, the neutral region, also the damping wing is suppressing some of the red part, just as I explained, right? So people typically define the effective transmissivity of IGM by just taking the transmitted flux and dividing it by the emergent flux. In this case, I ignore the blue peak part because they always get suppressed anyway. So people typically define it this way: red peak, intrinsic red peak, dividing the transmitted red peak. And obviously in the simulation, I'm not limited by any like sightline observational direction. So we have like 1,000 galaxies in each snapshot of redshift 6 to 10, and we can shoot line of sight in many different directions. In this case, 2,000 directions per galaxy. Therefore, I end up with like 10 million calculation of this kind of Riemann alpha transmission. So that was the methodology. I'll get to some point here. So starting from the easy one, I told you I'll be talking about the Riemann alpha offset. So if you look at the transmitted flux, this is only one of these 10 to the 7 samples, but this is very representative. So if you look at one of them, they typically have an offset between the Riemann alpha resonance and the actual emission. And that's puzzling because on the blue side is understandable. Blue side, they will all redshift to the resonance. But why are some of the photons on the red side get completely observed? Now that is because if you actually look at the velocity field of the gas around the galaxy, they're always usually isotropically infalling. And that's the reason is obvious. Galaxies are peaks of density, right? And that's how they formed, right? Galaxy formed as the matter infold into the density peak. So if you actually examine the velocity field around the galaxy, they will always be infalling. Because of that, in the rest frame of the infalling gas, this part of the profile will look like blue side photons, which will redshift to the resonance at some point. So the offset actually gives you how strong the infill velocity is. And infill velocity is given by the mass of the halo. So this is telling you that actually if you can measure this velocity offset in Lyman alpha, you constrain the halo mass, which is very difficult to do with observation. So in principle, you can constrain MUV versus halo mass relation with this kind of observation. JWST is already starting to see it. The main challenge of observing this is that you have to know where the resonance should be exactly. That means you have to measure other emission lines. And in order to measure other emission lines, you need very clean measurement of infrared spectrum, which only space telescopes can do. So, but then JWST is limited by its relatively small aperture. So they have good measurement of the offset, but as you can see, the signal to noise ratio is not great. So maybe this is something ground telescope can help. These future large telescopes can help, right? They will measure the high signal to noise ratio profile, then JWST will pinpoint the systemic redshift, and then we can hope to measure halo mass from them. Now, I'll move on to the next part. So let's examine the general knowledge, right? How the transmission depend on redshift and the brightness of the galaxies. This is from one galaxy at redshift 4 when the universe was 50% ionized in the simulation. The red line is the average transmitted profile. The blue shade is the 1 sigma range from 2,000 sight lines. And in the right is the same galaxy but at higher redshift of redshift 8, 13.2% ionized. You obviously see, the transmission is weaker as we expected. There's nothing strange about it. And also you compare bright versus faint galaxies, and even at same redshift, of course, the faint galaxies tend to have weaker transmission. So everything fits into the conventional picture, except that we provide more quantitative result. So this is another visualization, but now using all the galaxies. Here, x-axis is the UV magnitude of the galaxy. Each data point is one galaxy. The error bar is coming from 1 sigma range of 2,000 sight lines. You see from redshift 6 to 8, the mean transmission goes down as expected, and it goes down even faster for fainter galaxies as expected. Now, that's not the surprising part, but you see this gray shade here. This is giving you the 1 sigma uncertainty coming from different galaxies and different sight lines, which I find it very interesting. This, as you can see from the width of the shade, this Lyman alpha transmissivity has very large uncertainty range. So here, to talk about this uncertainty or the sight line variation, I now have 8 calculations of the Lyman alpha transmission from the single galaxy, 8 different directions. You see in one direction, you have 42% emission. Here in this direction, 21% direction. Even this is same galaxy, but depending on where you look at it from, the Lyman alpha line strengths can differ by factor of 2, right? Which observers didn't really think about. And that's basically because the universe is inhomogeneous, right? The H2 region surrounding a galaxy is not necessarily spherical because IgM density is inhomogeneous. The ionizing front will progress at different speed. And also you will have other neighboring galaxies where they form extra photons in some direction. And also the neutral part of the IgM will not necessarily have cosmic mean density. All these complexities result in this kind of scatter.
What is the redshift?
Yes.
What is the redshift here?
This is redshift 7, 50% ionized universe.
So, at a lower redshift, how it expect like similar kind of radiation, like 21 and 42? Let's say I'm talking about 5 or 4.
Redshift 5 or 4.
Yeah.
So this kind of variation will go away when the reionization finishes, because most of the opacity is coming from this blue region where the IgM is neutral, right? So when the reionization ends, we will not have any opacity from the neutral region. Yeah. Wenting?
So I'm curious, such a variation, how will this affect your way of using the Lyman alpha offset to infer the halo mass?
Yeah, okay, so there are two things going on here. Yeah, so the variation, there are two kinds of variation. The variation on this part, the damping wing part, which is coming from the fact that the H2 region is not spherical. And there will be some level of fluctuation in this offset depending on the direction. It's highly correlated with the halo mass, but still it's got some fluctuations. But I would say for massive halos, which dominate the local gravitational potential, the velocity offset will have less variation. So if you measure the exact profile, then you can still measure if you measure the exact offset, you can still constrain the halo mass, but the magnitude of the line will have a fluctuation, even for the fixed offset. There are two modes in the difference, right? Did I answer your question? Yeah.
I'm just curious, how robust you can infer the halo mass?
I think that in practice there will be some scatter that remains to be seen. So that depends on in different directions. So the question is how isotropic this infalling velocity is. They're more isotropic when the halo mass is larger, less isotropic when the halo mass is smaller. So I would say like relatively massive halos like 10 to the 13 solar mass each, they have fairly isotropic infall velocity.
I mean, you certainly have a large sample to
Yeah.
examine this.
Yes. So I looked at it. Basically, I say, yeah, it's given by circular velocity. In the paper, I show you the quantitative error bar. So for relatively less massive galaxies, 10 to the 11 solar mass, 10 solar mass, they are very uncertain because if you have another bigger galaxy next to you, then this isotropy will be disturbed and things like that. Yeah. More question? Moving on. Okay, so this is the probability distribution from 5 different snapshots. Probability distribution of the effective Lyman alpha transmission from individual sight lines, right? So you see, from red to purple, obviously there is a general trend. As you go to more neutral universe, less ionized universe, definitely the transmission is getting weaker. But then, as you can see from the probability distribution, if you only have 2 or 3 observations, you are never going to be able to distinguish green from red, right? So that means you need many, many galaxies to really constrain the center of this distribution and constrain how you ionize the universe is at the redshift you're observing. And I estimated that number to be at least 100 or more to constrain this neutral ionized fraction to 10% accuracy. And recently in JWST, there was some survey that actually tried to do this. So there was a survey called Sears and Jade. They separately observed Lyman alpha line strengths of 25 galaxies each. And then they found that the fraction was very different. From Sears, they found more than 50% had strong Lyman alpha emission. From Jade, they had like 20% strong Lyman alpha emission, which looked like highly discrepant result. But then if you consider this kind of huge scatter in the Lyman alpha transmission from individual sight line, it turns out that actually, as this black error bar suggests, they're within expected theoretical range. So it's not surprising to see this kind of scatter from only 25 galaxies. You need more than 100. Indeed, they're planning on now for the next step 200, doing this with 200 galaxies, where the error bar will be basically square root of 8 times smaller. So hopefully by then they will be able to really constrain how much the universe is ionized at a redshift of 7. Yes.
I suppose the Jade survey volume is much larger than Sears.
Survey area is much larger than.
Survey volume is from Jade.
Mm-hmm.
Larger than Sears.
Yes, they have different survey volume, the same number of galaxies. I think both surveys actually had a large enough volume to suppress the cosmic variance issue, although we looked into it. But then I would say it's more of the uncertainty in the individual sight line than the cosmic variance of the survey volume that is really giving rise to this discrepancy. That was our conclusion. Yeah. So now moving on to the next. I'll be discussing now about the Lyman alpha emitter cluster. So recently there have been very dense cluster of Lyman alpha emitters at redshift of 7.7, and most of the Lyman alpha emitter seems to be physically close to each other, which we found very interesting. So here is the redshift versus equivalent width map of this cluster. You see this. The brightest galaxy is shown as this red star is -22 in MUV, and then there are two other fainter galaxies which had extremely strong Lyman alpha. At redshift 7.6, we think the universe was much less than 50% ionized. So it was kind of interesting to see this high concentration of strong Lyman alpha emission. On average, we see less than 10% of the case strong Lyman alpha from galaxies. But here, almost all the members have strong Lyman alpha. And we discovered that the brightest galaxy has a slightly lower redshift than the other, meaning that if there is a big bubble formed by this bright galaxy, then the other strong Lyman alpha emitters must be sitting slightly behind. So maybe they're sitting on the backside of this large H2 bubble created by this bright galaxy, explaining why they particularly have very strong Lyman alpha emission, right? So, as you can see, if you see it sitting in the backside of the bubble, you have more sight line until you hit the neutral region. Therefore, the line will experience much less attenuation. So the motivation here is, okay, this is our imagination. Do we see this in the simulation? And what can you learn from this? So this is our simulation. So here you see this red star. This is a bright galaxy, -22 MUV. And this is a fainter galaxy, -20 MUV. Now, if you calculate Lyman alpha transmission along the direction of bright galaxy, you have 50% transmission. If you calculate the Lyman alpha transmission in the other side, you only have 5% transmission. So this is actually kind of a case which looks very much like our imagination, right? So just to calculate the angular dependence, you can always weight the transmission by the inner product of your line of sight and direction of your bright neighbor and integrate over the entire sky. We find that on average, toward the direction of your bright neighbor, 40% excess in transmission. Of course, this is a particular, most extreme case. I looked at hundreds of galaxies which fit into our imagination and brought the case. So we did that for entire sample of galaxies. We have 1,000 galaxies. We can investigate every possible pairs of it. So this plot is showing you, for example, on the y-axis is your transmission compared to the global average, and the black dots are from individual pairs. So the black dots are, so I visited every galaxy, faint or bright, and inspected if they had a bright neighbor, what is the distance to the bright neighbor, -21 MUV in this case. And if you have this scatter plot, you clearly have a trend. You have excess transmission when you're within 5 megaparsec of a bright neighbor around the -21 MUV. And if you check when the bright neighbor is less bright, maybe -20, -19, then the excess transmission gets weaker and weaker. So definitely the bright neighbor seems to be statistically giving you a significant boost. And basically, based on this fitting line, we conclude that in this case, this is redshift 8 universe, by the way. In this case, on average, just by being within 5% of within 5 moving megaparsec of a bright neighbor, you get on average 50% more Lyman alpha emission transmission through the IGM. And of course, we also check the directional dependence. So now, if whether you are behind your bright neighbor or in front of bright neighbor, we also checked whether that makes difference. And actually, the difference was much smaller than we initially thought. The case I showed you was an extreme case. On average, if you are behind the neighbor, you get 5% more boost. So it's more important that you are close to the bright neighbor than where you are in the bubble, but still. And of course, if you compare different redshift 8 versus 7, the boost from bright neighbor is much stronger at redshift 8 because higher redshift universe, the universe is more neutral. Only around the bright neighbor you get some transmission and not anywhere else. So this kind of strong dependence on the neighbor can be seen as a sign of how much the universe is neutral or ionized. and they will be reflected in the clustering of the LA, which I will be calculating as the next step. So that was for the LA cluster. Now I'm moving on to the double-peaked LA case, which is another very interesting topic. So in the beginning of the talk, I told you that low redshift Lyman alpha star-forming galaxies show double-peaked Lyman alpha emission, right? But you do not expect to see this kind of double-peak at redshift of 6.6, and I explained to you why. So, this even if you had a double-peak, the blue flux on the blue side will be redshifted to the Lyman alpha resonance at some point, right? And at the resonance, the cross section is very high, and you typically at this redshift require the neutral hydrogen density to be less than 10 to the minus 10 per cubic centimeter to avoid absorption at the resonance. And at redshift 6 or 7, typical hydrogen density is 10 to the minus 4. So you need to have ionization fraction of less than, neutral fraction of less than 10 to the minus 6 in the H2 region. But this is very difficult to achieve. Typically, the neutral fraction, even in the H2 region, is still 10 to the minus 4 or 5. So you still have like 1 or 2 orders of magnitude higher density to allow transmission of this blue peak at redshift of 6 and above. So when this case was found, it was very puzzling. It was first found by a ground telescope called VLT. At that time, they were not sure the resonance was right at the center. So they postponed their conclusion, but then recently by JWST, the infrared spectrum gave you confirmation of other emission lines, so they could pin down that the resonance was actually at right between the two peaks. Therefore, this one is a blue peak, which we thought was impossible to transmit in the high redshift universe. So they tried to explain this case, and basically they couldn't, right? So first of all, the galaxy itself, called CoDa 1, it's like minus 22 MeV. It's one of the brighter galaxies, but not crazy bright. It's not like quasar. They're not bright enough to achieve that level of high ionization in the surrounding. And there are neighboring galaxies that are much, much more fainter, so they're not going to create strong ionizing field. And then, yeah, they thought maybe, okay, this galaxy looks like minus 22, but maybe it had bursty star formation. It was much brighter. Of course, you can never test the hypothesis. And then also they said, okay, what if the universe was somehow much lower in density? Then maybe that could have happened. I'll be exploring that possibility in the next slide. So again, the motivation is similar. I'm going to inspect our simulation to see if we can see any case where this kind of blue transmission can happen and discuss what we can learn from it. So again, I inspected hundreds of galaxies and found the case. So here, zooming in from left to right, there is a galaxy at the center of this bubble. And if you shoot the sight line to this particular direction shown by this white arrow, actually it turns out that the transmission on the blue side can happen to some extent, just somewhat similar to the observed case, right? So I looked into what's happening with this particular sight line. If you look at this color contour, you see it's dark red here, meaning that it's, the neutral hydrogen density is almost as low as 10 to the minus 10 per cubic centimeter, the condition required to allow blue side transmission. And I looked into why. It turns out that this part was low density part of the universe. It's only 20% of the cosmic mean density. And when the density is lower, the neutral fraction is going to be proportional to the density you have. So therefore, if you look at the neutral hydrogen density, actually it depends on the square of the local density. So by having 5 times lower density in this void, actually you get 25 times lower density in neutral hydrogen. Therefore, although in in the rest of the universe, the neutral hydrogen density was 10 to the minus 8 or 9, in this particular region, the neutral density was down to 10 to the minus 10. This is obvious, right? Because universe is inhomogeneous. We have overdensity, low density. This is a bit rare because you have underdensity right next to a big galaxy, but it statistically does happen. So it's just that rarely your sight line can go through this configuration, and then you have a transmission in the blue peak. So I asked, what is, but this is a simulation, there are uncertainties. So you'd ask whether this is reliable or not. I would say existence of void, this is purely gravitational dynamics mostly. So there is no doubt about it. But then the ionization level within this void can be uncertain, right? Because it depends on the ionizing background, which is coming from the simulation and we don't know. So actually I decided we can actually use that fact to constrain the ionizing background of the universe. At redshift 6.5, we don't know the value. In the simulation, it's 0.22 times 10 to the minus 2. We use this gamma minus 12.2 to define it. And the density field of the universe is not going to change much. You know, gravitational dynamics we know very well. But then the ionizing background intensity can be different from what we assume in the simulation. So we can try rescaling the neutral hydrogen density by assuming the ionizing background density was stronger or weaker, and see what is the chance of seeing double-peaked LAE at different ionizing background. So in our default case, we have 1% of sight lines showing this kind of double-peaked Lyman alpha emission. But if you increase or decrease the the ionizing background, then your chance of seeing double-peaked LAE changes sensitively. So I realized actually by kind of constraining the fraction of double-peaked LAEs at high redshift, we can actually put constraint on the strength of ionizing background intensity. We only have a handful of cases, so we cannot do statistics with it, but with JWST and other ground telescopes, we'll definitely have large data, and we can count the fraction of double-peaked LAEs and definitely put constraint on this. So before moving on to the next, I can take some questions because the last part is the longest. Yes?
Yeah, so in all this, if you consider the neutral gas inside the galaxy, how the scenario changes?
Yeah, so neutral gas inside the galaxy, that's an important question. So going back to the beginning, one of the general assumption is that, okay, yeah, so as I explained in the beginning, our simulation is not able to simulate internal structure of the galaxy. Therefore, we are taking it as a black box, and then we calculate what's happening when whatever the light is produced, what happens to them in the intergalactic medium. But of course, that the internal process, the galaxy ISM, CGM is also another big uncertainty here. So here I'm going to just say this emergent flux is the result of whatever was happening within the virial radius. But the process you described will definitely have an impact on this emergent flux, and this emergent flux has huge uncertainty, by the way, which I didn't address here because I'm only looking at the IGM. So that will have big impact. For example, I said sightline variation from the IGM is this amount. Actually, the variation will be even larger because actually we have extra uncertainty coming from internal process of galaxies, which will change the emergent flux. Okay, other question? Moving on. Okay, so the last part of this talk now is about the galaxy damping wing observation. So I've been talking about Lyman alpha emission, the very narrow Lyman alpha emission spanning maybe 1 or 2 angstrom, which I show as this green line here. But now JWST is starting to measure the continuum of galaxies. I mean, continuum of quasars have been observed at high redshift many times because they're brighter. But then now they're starting to see continuum of galaxies. And now if you look at the continuum, you see this significant absorption around Lyman alpha, and presumably coming from the damping wing part. People have been using this feature to constrain reionization for quasars because quasars are brighter. But then the problem with quasars is that the shape of continuum for quasar is complicated. It's got very broad line emission and so on. You can model from the red side and then extrapolate to the blue side, but it has a lot of uncertainty. Whereas in galaxies tend to have much simpler shape. Like the line tends to be super narrow, only a few angstrom. So if you get to the red side of the line, you almost have power law-like very clean shape. So ideally, you can almost recover the transmission curve from these galaxies without any uncertainty coming from the internal structure of the galaxy you mentioned and all the near complexity from the nearby inhomogeneous universe. So this is an example at redshift of 10 by this author, so observers started to raising this question. So can we constrain reionization, the ionization state of reionization with this kind of damping ring feature in the galactic continuum? So for this galaxy, they failed, and the reason is so they tried they tried modeling the IgM damping ring from their model, and which is this red line here, and it looked like it still have much higher flux than what is observed, the black line. So even 100%, so this damping ring was stronger than the IgM opacity of the 100% neutral universe, which was puzzling. But then they realized, maybe in these galaxies, in the ISM or CGM, there can be very dense gas clump blocking the sight line, star forming clouds or infalling gas from the CGM. If you assume this kind of pointer-like observer and add to it, then you kind of explain this continuum shape of the highest universe. So this is a complication. Like the shape of the SED itself seems to be very simple, but unlike quasars, these galaxies seem to have this extra damped Lyman alpha observers in them, which is adding extra opacity. So again, I decided to explore with my own simulation with my observer friend if we can model this galactic damping ring from high redshift, and can you really constrain the reionization history with it? So again, from the simulation, we calculate a bunch of Lyman alpha transmission curves for different sight lines. So I'm only showing you the subset of it. Purple, 1% ionized universe, red, 100% ionized universe. They have a scatter from different sight lines, which I express in terms of multiple lines here. And then I'm going to bin the data into low resolution spectrograph, spectral resolution of 100. This is typical resolution for the low resolution spectrograph of JWST. And I'm going to make it more realistic by adding noise. So here I add 5% random Gaussian noise to every data bin. This roughly corresponds to signal to noise ratio of 20 for each spectral bin. And then finally, I add the damped Lyman alpha observer component, which seems to be in the ISM or CGM. And you can see now you have more scatter. So suppose, you pick this, you look at this black line here. It's obviously from the group of green line, right? Now, the question is, given this spectrum, can you tell if this black line came from the group of green line? That's the question we are asking. Given this mock observation, are we able to constrain which universe, which ionized fraction it came from? So of course, we try different noise levels. Observational condition differs from observation to observation. This would be 1% noise, signal to noise of 100, and this would be signal to noise of 5. We will typically have somewhere between 20 and 5. 100 would be unrealistic. So I'm going to show you how we do this. So first of all, we plot this scatter. We create a scatter plot of first two data bins, and I'm going to explain you why. So you can see by adding these DLAs, it's very difficult to recover which ionization fraction these curves come from. But if you put that in this data space, the opacity from DLA, so these circular dots are from DLA-free galaxies, and these X symbols are from DLA-added galaxy. So you can see they have different distribution. So if you just look at DLA-free galaxies, these dots, from 100% to 1%, you can see the opacity is moving in this direction in the data space, whereas if you add DLA opacity, it's got slightly different direction. So if you look at this frequency dependence, you can still tell one from the other. You can tell which one is contaminated by DLA, which one is contaminated, which ones are not contaminated by DLA. And the example case here would be the black star here. And we can kind of still see, maybe this must have come from the group of green dots. Now I'm going to create a machine learning model. So basically, when you're looking at this with human eyes, I guess you're trying to draw a boundary between groups of points, right? So when you're given a random observation, we'll try to tell which color it is from. I'm going to do that with the machine learning model. So I'm going to give you a brief example. So suppose you come up with this very crude classification. There's this decision tree. This is basically tell you if the point is on the right side of this number, then it's red, yellow, green, blue, magenta, right? And this is going to work for the most of the time. It's not perfect, but then you can think of having a criteria like this. And the machine learning algorithm that I'm going to use is something called random forest classifier, which is collection of decision trees that I just described. So it has hundreds of decision trees, which are by itself is imperfect. But then it has an automated algorithm to generate a lot of imperfect decision trees. And at the end, you take a vote for individual trees to determine for a given data point which ionization fraction it belongs to. So here I'm showing the decision boundaries coming from this decision tree algorithm. There are two things going on here. You have brighter background, darker background. Brighter background means it's DLA contaminated. Darker background means it's not DLA contaminated. There's one tree, and there's another tree which determines the ionization fraction. So yeah, I mean, corresponding color, right? It's magenta background means it's from magenta points. It's blue background coming from blue point, right? So here there are a lot of things going on. And by the way, I'm only showing you this 2D classification, but actual calculation is done with all the 8 data points I have here. This 2D demonstration is only for visualization, by the way. But first 2 data points give you the most of the information. The other points are like minority reports. So here are important takeaways. So just by looking at this bright versus darker background, you can immediately see the random forest classifier is very well separating the DLA contaminated samples versus DLA free samples. The accuracy is actually 96%. Now then you ask, what about the ionization fraction classification, the Q classification? I looked at 2 different samples. So if we calculate the accuracy for this X symbols, DLA contaminated sample, accuracy is only less than 50%. But if you look at the accuracy for DLA free samples, the accuracy is above 80%. This is telling you that for DLA contamination definitely makes the classification very difficult, but we can identify those DLA contaminated samples and exclude them from the analysis. So if we exclude DLA contaminated sample and use the DLA free sample, we can accurately still constrain the ionization fraction from damping wing observations. So of course it can be done for different noise level. I show you the most noise-free case of 1% noise. If you increase the noise level, things are getting difficult. 5% case, you have almost below 30% accuracy for DLA contaminated sample, only 60% for DLA free sample, but still at noise level of 5%, signal to noise ratio of 20, things are working. But noise level of 20, yeah, it's a mess. There's nothing going on. So this is another way to show you. So this is the histogram. So suppose you throw damping wing from 100% ionized universe and you run your random forest classifier, and what is the distribution there actually classified. So when it's on low noise, signal to noise of ratio of 10, most of them are correctly classified. But if you go to 20% level, now they're more broadly distributed. Like they're kind of randomized and prediction fails more and more. But you're kind of seeing how it works. And if you compare the highly ionized versus less ionized universe, you can kind of see this blue and magenta contour being higher, meaning that the damping wing is more effective in constraining this at early time of the reionization. When the neutral fraction is higher, ionization fraction is lower. Because the damping wing has higher sensitivity when the universe is more neutral. So we built this machine learning model, and we applied it to actual galaxies. So this GNZ11 is one of the most famous galaxy observed by the JWST. It's from redshift 10.6, extremely high redshift, but it's extremely bright at the same time, so they actually have very accurate measurement of the damping wing. It's much smaller than the Milky Way, 25 times smaller in size, 100 times smaller in mass, but 20 times in the star formation. So there is this continuum here, and I collected the data points near the Lyman alpha emission, and this is the signal to noise ratio, which is reaching almost 20. So this roughly corresponds to 5% noise case that I showed you. So here is the general pipeline. So again, this is the normalized damping spectrum. This is the noise. And now, starting from our simulation, we create mock data by adding noise according to the signal to noise ratio of the observation. So our mock data is specifically tuned for this particular observation of GNZ11. And again, I look at them in the data space. I train random forest classifier to determine their ionization fraction in the neighbor. And we find that this galaxy is not contaminated by DLA. It's in the darker side of the colored background. And it's obvious that they're in the middle of this magenta dots, meaning that they're most likely from the universe, which is almost neutral, 1.6% ionized. So the prediction probability indeed says with 98% confidence, it's more like this most neutral snapshot of the universe, which translates to the upper bound of less than 7.4% ionization at redshift of 10. So I won't describe it. Yes, go ahead.
So this DGA is in the axis?
This is a wavelength in the unit of velocity. A wavelength difference compared to the resonance. So roughly speaking, 400 is like 400 kilometer per second is like 1 angstrom. So yeah, this is like 60 angstrom from zero. Yeah, sorry. So any other question? Yeah. So this is coming from the publicly available JWST spectrum. There are more, but the signal is not as good as this one. So, but I tried inspecting all of them. So this upper bound is coming from GNZ11, and also there are other galaxies. This is a lower bound, which is very weak. It's only excluding this small part of it. So it's not really ruling out any reionization model. This line is coming from our own simulation. But you know that, even if GNZ11 is putting tight upper bound, most models say universe is almost neutral at this redshift anyway. So it's not really distinguishing. But we will have better data in the future. We will have higher signal to noise ratio. We will have more galaxies. So maybe, hopefully, we can shrink these error bars and start rejecting some of the reionization models and so on. So that will summarize my talk. I looked into different aspects of Lyman alpha emitters or Lyman alpha photons from the high-res universe in the simulation. And I think there are a lot of interesting, promising cases. With future data, we can learn much about the reionization. Thank you. Yeah.
Well, I'm curious about the DLAs.
Yes.
I suppose in your simulation you cannot simulate them.
Right. So here we are kind of adding it artificially. So obviously it's a point-like observer, right? So it's only the column density that we need to know. And column density, I choose some flat distribution between 10 to the 21 per square centimeter and 10 to the 23, roughly coming from recent work. There were recent work which were really focusing on the strength of DLA from these high Z galaxies. And they roughly find somewhere between 10 to the 23 and 10 to the 20 evenly distributed. So I'm randomly populating DLAs in our sample galaxies based on the distribution. Things can change depending on what you assume about them. Yeah.
Another question is how do people get the upper limit or lower limit for your last plot?
Okay, so you are questioning these data points, right? I'm gonna open my hidden slide then. Okay, let's see this one. So it's basically, no, not this one. 7 point. Okay, I'm gonna unskip this slide. Play. Okay, yeah. So that data point is coming from this particular galaxy redshift 8. And as you can see, actually, it doesn't have a lot of data points. And the noise is less than 20, above 10. But we still run our algorithm, and you can see what's happening here. Come on, calm down. Okay, so it's easy to see from this data space, right? So this is our data point, and this black star is this observation. You can see that it's kind of sitting where between red and blue distribution of dots. So it roughly corresponds to this 4 colors, except the magenta. So you reject the magenta part, which is a very highly neutral universe, and then in the rest of the other 4 snapshots, it can be anything. So therefore, we get the lower bound, only rejecting the magenta case, and the rest is all the rest is possible. That's what we are getting here. Yes.
With all this, what is your conclusion of when the reionization ended?
So actually, this particular, are you asking about this damping wing or as a whole?
The other one, like without the damping.
Yeah, so end of reionization, actually, it depends on what you define the end of reionization. But I guess roughly speaking, for example, in the simulation, if we no longer have this blue region, then we call it end of reionization. There are constraints coming from, say, Lima alpha forest and so on. But it's difficult because, for example, Lima alpha forest can saturate even the universe is highly ionized, because when the neutral fraction is, say, 0.01%, then there's a Lima alpha transmission. But if it's 0.1%, then it will be observed. So it's hard to tell. But roughly, people are nowadays thinking redshift 5.5 is rough end of the reionization. In this Lima alpha emitter business, we are not good at constraining the very end, because it's hard to define, right? Whether the last 1% of the neutral part, when does it get ionized or not, is kind of uncertain. Roughly 5.5. Yeah.
Okay, I guess it's about time. So Hyunbae will be staying until this Friday, and his visitor's office is 11:03. So you can bother him. Please bother him. So let's thank him for his nice talk.